Hello everyone, welcome back to OpenGL. Today we're going to be switching gears from our our adventure into advanced lighting, and we're going to return to collisions, and we're going to create a more general collision system, one that will account for any type of transformation, including rotations. So currently we have our collision models look like just they're simply axis-aligned bounding boxes and spheres. And this is good for something like a course check, where you just want to see if two objects are colliding, but you don't want to see where they're colliding or in what direction. So that's one limitation. And then another limitation is where when we have transformations and rotations, then that axis-aligned bounding box is no longer axis-aligned, and it becomes a little more tricky in how to determine if a box is colliding with a sphere, and if a sphere is colliding with a box, so on and so forth. However, with the sphere, that will all stay the same. So we're going to look at a new collision model, and that's pretty much what it is. It's called a collision model, which are essentially simplified meshes, where they are built in some program like Blender, like any other 3D modeling program, and they are just specified with vertices. And the point of it is to have a lot fewer vertices in the actual model itself, as to reduce the amount of data required, because you can't just go ahead and check every single plane on an object. That would be way too much. So you're gonna have a collision model with a list of vertices and a list of indices, and then with and this will be good for something like a finer check, where you want to determine how an object should react to being collided with, because you can determine exactly where it's being collided with. So we're first going to look at this here. So we have a triangle defined by 3 points, and that's what our model will be, pretty much just a list of faces. And so let's just assume that this is one of the triangles in our collision model. So we have P1, P2, and P3, and then I have vectors between P1 and P2, P1 and P3, and then P2 and P3. And then there's a plane that connects them all, and that plane is defined by the normal vector, which you can find by taking the cross product of the vector connecting two of the points. So P1 and P2, and then P1 and P3, but that first point has to be the same. So you can't take the cross product of P1 and P2, and then P2 and P3, because you would get the negative result. So we're going to be looking at this, and then we will also be looking at how to incorporate or how to use this plane here to determine what collisions are. So let's start by looking at just the plane itself. So we start with our 3 points. So we have P1, which is 0, 0, 1. P2 is 0, 1, 0. And P3 is 1, 0, 0. So now we have our vector A, which is equal to P1, P2, so the vector from P1 to P2. And this is going to be equal to 0, 1, negative 1. And then we have our vector B, which is the vector from P1 to P3, which is equal to 1, 0, negative 1. I'm just subtracting the values of P1 from P3. And then C is equal to P2 to P3. And this is going to be equal to 1, negative 1, 0. Now our normal vector, which we will use to define the plane, is going to be defined as normal is equal to A cross B. Now the cross product produces a vector that is perpendicular to both the input vectors, and that's what we want. With our planes, the planes are defined by whatever vector is normal to them. So the plane is the set, or the span of, in 2D, of all vectors, or pretty much all vectors that are perpendicular to some other vector called our normal vector. So if we have two vectors in the plane, A and B, which is what we have with our model here, A and B are in the plane, we want to find the vector that is perpendicular to both of them, which is going to be the normal vector for the plane. And you can find this using the determinant of this matrix I, J, K, which is are the unit vectors, and then we just put in AX, AY, AZ, then bx, by, and bz. And if you solve that determinant, I'm not going to go into the details of that right now, but you'll get negative I minus j minus k. Now our plane equation will look like some point on the plane, so we'll call it P1, and then the vector from P1 to P, which is just a general point, dotted with the normal vector, is equal to 0. And this is just because if you have a dot product and it's equal to 0, then the vector is perpendicular. So once again, all the vectors on the plane are perpendicular to the normal vector. So if we take a vector from one point on the plane to another point on the plane, that should be perpendicular to the normal vector in order for the point to be on the plane. And we can simplify this to, it's going to be P minus P1 dotted with n is equal to 0, and then using the distributive property, we can make this n dotted with P is equal to n dotted with P1. So this form will help us out later on. And then just to expand this, I'll just write it out here so we can see what it'll be in our case. So nx times x plus the y component times y plus nz times z, where x, y, and z are the general values, and then nx times p1x, which is our known value, plus ny p1y plus nz p1z. Forgive my bad handwriting, but yeah. And with this, we now have a plane. So if we plug in our values, we have that the plane P, or I'll call the plane pi, capital pi. It's going to be the equation for this is going to be negative x minus y minus z is equal to negative 1. And this is just through plugging in values where x, y, and z are kept as general values. And this is the blue plane here. So we have minus x minus y minus z is equal to negative 1. So that plane goes through all 3 points. So that's how we're going to determine the plane. And what's advantageous here is, since we have the normal vector, that can be rotated and transformed wherever we want it to go. So that if we have the transformation matrix for our model, what will happen is we can just apply that same matrix to the normal vector, and it will give us the accurate plane that still goes through each of the points. Alright, so this is our plane. Now let's consider another set of points here. So we'll have we have U1, U2, and U3, which are these points in blue, and then we have the vectors through them as well, so D, E, and F. And let's say that we want to determine if the plane, or I'm not going to put the plane onto the screen, but let's say the face made by U1, U2, and U3, if that collides with the face made by P1, P2, and P3. Now, the gist of how we do this is we essentially just have to check for each of the vectors if they intersect with the face. So from here we can clearly see that the vector from U2 to U3, or F, intersects directly with the face made by A, B, and C, or P1, P2, and P3. So we should expect a collision here. So we're going to go through each of the vectors here, D, E, and F, and determine if they collide, and we'll see some special cases and what we can do with that. Alright, so once again we have our points U1, which is -1, 1, 0, U2, 0, 0, 0, and U3, 1, 2, 0.5. Alright, and then we have now our vectors D, which is equal to U1, U2. And this is going to be equal to 1, -1, 0. E is equal to the vector from U1 to U3. And this is equal to 2, 1, 0.5. And then the vector F is equal to U2 to U3, which is 1, 2, 0.5. And we are using, because we're looking at to determine if these vectors intersect with the plane, we want to know not what their vector values are. We want to know what their translated values are, because we can consider this plane as centered wherever, it doesn't really matter, but we don't want to consider the vector E as originating from the origin, because it's not. It's originating from point. It's kind of hard to see here. This is I'm also screwing with the rotation right now, but you can kind of see here how the vector E comes from U1 and goes to U3. It doesn't come from the origin, so we want to know the line going through U1 and U3, not just the vector. So we can use this vector, however, to determine the line equation, which is just going to be the D, I'll just call it line D, is going to give us the point P, which is just a general point, is equal to U1, the starting point, plus U2 minus U1 times T, where T is a parameter. And this can also be written as U1 plus D times T, where D is the directional vector. And then similarly, for E, the line going through this is going to be a general point is equal to U2, or U1 rather, plus E times T. And then F is going to be the general point is equal to the starting point U2 plus F times T, a parameter. Now, if we want to determine the intersection of lines, not just vectors, of lines in a plane, all we have to do is just plug in this line equation, which would give us a point, and plug these values into the plane equation, which we have right up here. So we'll first check for the intersection of D with the plane pi. And in our case here, we expect no plane intersection, because D is parallel to the plane. So if we see here, D is this vector over here, and it will never intersect with the plane, and I intentionally chose these values. So let's just plug it in. So plug in the line equation, which individually we have our components. So Px is equal to the x, the general x, which is equal to U1x plus U2x minus U1x times the parameter t. So we get that nx, the x component of the normal vector of the plane, times the x component, so U1x plus U2x minus U1x, or I'll just write this as E, or as dx, dxt plus ny times u1y plus, this is going to be the same thing, so dy times t plus nz times u1z plus d, the z component of d times the parameter t, and this is going to be equal to nx p1x plus ny p1y plus nz p1z. Now when we solve for t, because that's our goal here, we want to solve for the parameter value that will give us the intersection here. So whatever value we get for t, that will be the parameter of the line at the point of the intersection. So solve for t, and what we'll get is t is equal to nx times p1x minus u1x plus ny p1y minus u1y plus nz times p1z minus u1z, where once again the point p1 here is we're going to consider as the origin of the plane, and this is all over nx times dx plus ny times dy plus nz times dz. And if we kind of analyze this equation a bit, what we're going to see is that the numerator is equal to the normal vector dotted with the vector going from u1 to p1. And then the denominator, so this is over n dotted with d. That one's a little easier to see. But in a quick explanation for the numerator, we just have the x component of the difference times the x component of the normal vector plus the y component of the difference times the y component of the normal vector plus the z component of the difference times the z component of the normal vector. And this will hold. This equation is general. It doesn't care about what the values are yet. These are just general equations. So now if we look at our values, so calculations here, we see that t is equal to negative 0 minus 1 minus 0 plus 1 minus 1 minus 0 all over minus 1 minus 1 minus 0. And these are values that I got just from looking at the equations, what values they wanted, and then I used the values from our givens and the normal vector as well. And this is going to give us a negative 1 over 0. And if we want to look at this equation or this result as a more general, in a more general context, we can see this as a real number not equal to 0 over 0. Now what does this mean? This means that there is no planar intersection at all. Why is that? So if we see n dotted with d, so n dotted with d, the denominator is equal to 0. Therefore, n is perpendicular to d. However, n dotted with u1 to p1 is not equal to 0. So therefore, n is not perpendicular to u1, p1. So therefore, the vector going from u1 to p1 is not on the plane. Because for it to be on the plane, it would have to be when it dotted with normal vector, it would be equal to 0. Right? So as a result, because it's parallel to the plane and that direction never changes, this vector will never be on the plane. So there was no planar intersection at all. All right, now let's check the second vector of our second set of points, so the vector e. And when we look at e, we see that e will intersect the plane at the value, at a good value here. So it's going to intersect the plane in between u2 and u3. So let's check this out here. However, it is not in the face. So there's going to be a few cases that we have to look at here. So now we're looking at the vector e with pi. And we expect planar intersection in range. I'm going to say in range, meaning in between the 2 points, so it's a valid intersection. And then also, or however, out of the bounds. Out of the bounds of the target face, of the face formed by P1, P2, and P3. So let's first calculate t, and we can use the same exact formula right here. So we can say that t will be equal to n dotted with, now we have to look at u1, p1, the same 2 points, because the vector e, or the line through e, originates at u1. And then divide this by n dotted with e, which is our vector that we're testing right now. And if we do the math, we get that this is going to be equal to negative 1, which we found before, over negative 2 minus 1 minus 0.5, which is equal to 1 over 3.5. And you have to keep this exact. Now, what we have to do with this information is determine if it's in range. So t is approximately equal to 0.28, which is in the range 0, 1. So therefore, it intersects with the plane between u1 and u3. Well, how did I know that? Well, if we look at the line E, at P, or when the value of the line at t equals 0 is just going to be the value u1. So if we look at this equation for our line here, we have P is equal to u1 plus the directional vector E times the parameter t. So if we plug in 0 for t, then we just get the initial point. And then P1, point evaluated with the parameter 1 is going to be equal to u1 plus E, but E is going to be u2 minus u1, so we have u1 plus u2 minus u1, which is equal to u2. So therefore, if the parameter is in between 0 and 1, the point will be in between u1 and u2. So therefore, it is a valid intersection with our current face. So it's in between the points that we're looking at. But this isn't the whole story. Just because the value is in between there doesn't mean that it intersects in the face. That means that it intersects in the plane, not the face. So what we have to look now is determine if in a triangle P1, P2, and P3. Alright, so now we're going to look at a new concept called coordinate systems. So let's assume that we have, so in our Cartesian system we have the origin, which we'll call point P1, then we have point P2, and then a point P3. And then we have our unit vectors I, which we'll call A, and then J, which we will call B. And this is our vector C here, or yeah, it's this way. So for a point, let's call this point P. For this point to be inside the triangle, we have to determine the vector from P1 to P, like that, and determine if the components of P, in terms of of A and B, are within some bounds here. So we can look at this as P, or P1, or sorry, P1P is equal to some multiple of A, x1, times A, plus some multiple of B, x2, times B. And this is pretty much our rectangular coordinate system. This is just equal to x1 times I hat, plus x2 times j hat, which would give us the coordinates x1 and x2. If we wanted to call this x and y, this would make a little more sense here. So xy, x, y, and that would give us the coordinates xy in the xy plane, which is exactly what we know. Now, what if, now this is a very simplified example. So when we do find these values, what we have to know is that, so what makes the values of x1 and x2, what makes that a valid point? So if we look at this here, we first have to determine that x1 and x2 have to be positive. So x1, x2, or I'll say xy, must be positive. Just because if the point is down here, P1P would have a negative component of A and a negative component of B. Just like that. However, we have this kind of, it looks like a shaded area that is valid. And because we've restricted it to positive values, we just have to look in this triangle right here. Well, what is this triangle? It's defined as the inequality x plus y is less than or equal to 1. And if you solve this for y, what you would get is y is less than or equal to 1, or negative x, plus 1. So this is just at every point below the line, y equals negative x plus 1, or every point below the line with the slope negative 1 and y-intercept 1. Right? So And once again, we've restricted the domain, so we'll only get a certain amount of values here. Now, this is entirely generalizable. Let's say we had, let's look at the general case. So we have P1, and P2 is out here, and then P3 is now over here, or else, yeah, right here. So this is our vector B, this is our vector A, and I'm no longer using I hat and J hat because they are no longer the unit vectors in the Cartesian system. But, so how is this going to help? Was this analysis here going to help us? Well, we can kind of use any two vectors that are not parallel and define our own coordinate system using those vectors. So let's think about this. So let's say we had, keep going, like that. At this point up here, this is going to be 3b, or 2b, and then 3b, then 4b, and so on. And that's the exact same as going out over here and calling this 2i, which is equal to 2a. And then, once again, we can go over here, 2a, 2b, or 3a, so on and so forth. So what we're going to do now is we're going to define our point P as equal to x1 times a plus x2 times b, which is the exact same equation that we got. And if you want a more comprehensive diagram, you can kind of see this here. It's kind of a slanted grid. So we take our rectangular shape and kind of shear it, per se. And let's call this point right here, let's look at this in particular. This is going to be one value of a, or one multiple of a, so this is a plus two multiples of b. So in this coordinate system, that would be 1, 2, because it's the linear combination is made of 1 of a and 2 of b. But once again, the same rules will still apply. The same analysis with determining the components. So let's make this a little bigger here. So we have here, so P3, P2. If we wanted to determine if it was in the plane here, if just some point P, once again we would have to say, alright, well, P1P is equal to some value x1 of a plus some multiple x2 of b, which is exactly what we had before. And then, once again, x1 and x2 have to be positive, because if we had a point down here, like this, that would be some negative value of a. This coordinate system also extends this way. This is negative a. And this here is negative b. So they extend beyond, just like the Cartesian system. And then, if we were to draw the line x1, x2, or the line, and determine what inequality this would represent, we would get that x1 plus x2 is less than or equal to 1. If we wanted to solve for x2, think of this here as our x2 axis, and this as our x1 axis. And we just have the inequality. Once again, x1 plus x2 is less than or equal to 1. So we're going to get that inequality, and then you can kind of see, all right, well, then if it satisfies both inequalities, then the point will be within the triangle. And this is this is pretty similar, or a simplified version of the change of basis matrix, which is relying on the same type of analysis here. So if we had our basis here, B, which is made up of the vectors A, B, and the normal vector, this would be a basis of R3, of 3D space. In other words, using a linear combination of these three vectors, you can get to any point in 3D space. And then we can put in the coordinates of B or of this here, so B. So we could say that using the matrix, using a change of base matrix, M, which is just has the vectors as its columns, so A, B, and N. And then to get in the coordinates, all you have to do is P in the coordinate system of B, which is equal to x1, x2, and x3, is M times the point P in Cartesian coordinates. So in other words, P would be equal to x1 times A plus x2 times B plus x3 times N, which are the vectors in the basis here. However, we don't need to do all this because this would require finding an inverse of a matrix, or this actually needs to be M, the inverse of M. So this would be a little expensive. However, we know that x3 is equal to 0. Now, why do we know that? Well, because we know the point is in the plane. Using the value of t, we determine that it's in the plane. So it does not have any component of the normal vector in it. So now what we can do is we have a simplified system here. So E, T, which I'm saying the line E, the line made by E, minus P1 is equal to P, which is equal to x1 times A plus x2 times B, which gives us 3 equations, one for each component, x, y, and z, and 2 unknowns. So, as a result, with any system, we get a matrix. So AX, BX, so the vectors as the columns, or as the columns. And then as the coefficients, we have E, T, the x component of the point, minus P1x, ETY, minus P1y, and then E at T, the z component, minus P1z. And then we have we reduce this using reduced row echelon form, or the Gaussian algorithm, and then we'll get 1, 0, 0, 0, 1, 0, and then we got our components x1, x2, and 0, and then we just have to check that they're both positive, and then x1 plus x2 is less than or equal to 0, or is less than or equal to 1. Alright, so using our values, we found that t is equal to, where is it? Up here, around approximately 0.28. So we have t is equal to 0.28 is approximately minus 0.44, 1.28, 0.14. And this is equal to u1 plus e times t. And then if we subtracted the points, so t is equal to 0.28 minus p1, we're going to get negative 0.44, 1.28, minus 0.86. And then we plug it into the matrix. So A, B, I'll call this P1 E at T, the vector there. If we plug in these values, we'll see it becomes 0, 1, 1, 0, negative 1, negative 1, and then the coefficients, or the solutions will be around 0.44, or around negative 0.44, around 1.28, and then around negative 0.86, but you have to keep the exact values here. And then if we reduce this, (1, 0, 0, 1), and then we get the components 1.2857, and then negative 0.4286, and 0 at the bottom. So x1 is equal to 1.2857, and x2 is equal to minus 0.4286. With x1, we had that it's greater than 1, greater than 0, which is good. However, x2 is less than 0, so no good. So that means there's no collision. Alright, so the vectors D and E do not collide with the plane at all, or D does not collide with the plane, so there's no intersection with the face. E does intersect the plane, however, it does not collide with the plane, or the face itself. Yeah, sorry, it collides with the plane, but not the face, made by the 3 points P1, P2, and P3. Alright, well, let's try F now. And we do expect that F is this, or that F is valid in both conditions. So F goes from P2 to P3, and it goes straight through the middle of the face. So we're expecting both a planar intersection and then a collision with the face. So let me just... So F with the plane pi, expect a planar intersection in range and in bounds. So once again, we calculate t. T is equal to n dotted with u2p1, where u2 is the originating, or is the first point on the vector f. This divided by n dotted with f. And we get that this is equal to minus 1 over minus 3.5, which is what we had before, which is approximately equal to 0.28. So that means, and this is in the range 0, 1, so F intersects with the plane P, or sorry, with the plane pi between U2 and U3. Alright, so let's do our calculations. So F, the line F evaluated with t equals 0.28, make sure it's the exact value 1 over 3.5. If you're trying to do this by hand, do not plug in 0.28. This is going to give us approximately 0.28, 0.56, and 0.14. And then if we subtract the point, so ft is equal to 1 over 3.5, I should actually just write that. This is approximately equal to 0.28, 0.56, and then negative 0.86. Alright, so we'll plug this into the same matrix. So we have our same two vectors, A and B. And this time it's going to be from P1 to F at T. And once again, this is just equivalently stating that x1a plus x2b is equal to P1f at T, and this expands into x1 times ax plus x2 times bx is equal to f tx minus p1x. x1 times a, the y component, plus x2, b, the y component, and then just use the y component for f minus p1, and then the same thing for the z. Alright, so plugging these into the matrix, we have same coefficients as before. And then this is approximately 0.28, approximately 0.56, and approximately negative 0.86. And then if we reduce this, we get that it's 1, 0, 0. 0, 1, 0, so that's all good. And then our values are 0.5715 and 0.2857 and 0. So here we see that this is x1 is equal to 0.5715 and x2 is equal to 0.2857, and these are both greater than 0. Or greater than or equal to 0. And also, we see that x1 plus x2 is equal to 0.8572, which is less than or equal to 1. So it is in the triangle, and oh my fucking god, we found a collision. So yeah, we found the collision between U2 and U3. So it's pretty cool. Yeah. Alright, let's try, there's still another case here that we can get with t. So we've looked at where t is a real number over a real number. Where the denominator is not equal to 0. And we've also looked at where the denominator is 0. So our next case is if we look at some other set of points. So we have our a vector g, which is equal to the v1 to v2, which are just random points, and where g is on the plane. And this is, we expect a complete planar intersection. And a collision. And I'm not going to do it for the non-collision, but we'll see it in here. So we see the same formula. T is equal to n dotted with the vector from v1 to p1, where v1 is the origin of the line, divided by n dotted with g. And since they're both in the plane, we're going to say this is 0 over 0. How do I know this? Well, if v1 is on the plane and p1 is on the plane, then the vector on the plane will be perpendicular to the normal vector. And the same goes for n dotted with g. So since they're perpendicular, the dot product is going to be 0. So we're looking at a 0 over 0, which is not that fun. But this means that it is in the plane. So now what we have to do is intersect g with each of the lines. Each of the bounding lines A, B, and C. So let's just look at G with A, and the process is the exact same for B and C. So if we look at the line definitions for G and A, G is going to be x is equal to v1x plus v2x minus v1x times the parameter t. And for A, it's the same thing. X is equal to p1 p1x plus p2x minus p1x times a different parameter s, because they are different lines. You need to make sure that you have the two different parameters, and then the same thing for y and z. So now if we set these equal to each other, so gx is equal to ax, gy is equal to ay, and gz is equal to az, we're going to get a system of three equations and two unknowns as before. So v1x plus v2x minus v1x times the parameter t is equal to p1x plus p2x minus p1x times the parameter s. And if we do this for the same, we'll find that we get the equation with the coefficients on the same side. So we have p2x minus p1x times s plus v2x minus v1x times, or I'm actually just going to use the vector components here. So gx, sorry, not gx, ax times s plus gx times t is equal to v1x minus p1x, so on and so forth for x and for y and z. Once again, we have three equations, two unknowns. We have our matrix. Ooh, this should actually be axs minus gx. So we look at this ax, ay, az, and then we have negative gx, negative gy, and negative gz. And then the constants are going to be the vector p1, v1, the x component, and p1, v1, the y component, and then p1, v1, the z component. And if we reduce this, there are two possibilities here. So we either get that the matrix is inconsistent. Now, if you've taken any linear algebra, why would this be inconsistent? Well, first of all, we see that this would mean that s and t are equal to 0. Alright, sure, but that would mean that that v1x and p1x are the same. However, we have this bottom row here, which is not okay. So this would mean that we have az times 0 minus minus gz times 0 is equal to 1. Now, how does that work? 0 minus 0 does not equal 1, so therefore inconsistent. So therefore, no intersection. Now the other possibility is that we have a consistent system here. Same result in the coefficient matrix, however, the constant matrix will give us s and t, respectively. And there has to be a 0 in that bottom row. So, once again, we perform the same exact checks. The checks will be the same. However, we do have to have one more check here. We need to make sure that t and s are between 0 and 1. It's not enough just for them to be positive, because these values have to be for the same reason that when we calculate t here, that it has to be between 0 and 1. So therefore, to be for the intersection to be within the points. All right, good. So that's let's do a quick recap. So we'll start at the top here. For 3 points, P1, P2, P3, we get the vectors that connect them. We get the normal vector using the cross product, which defines our plane that holds all 3 points. Then we have another set of points here, and I will just move this over here. Another set of points, another set of connecting vectors, and then we have their line definitions. And if we want to determine if two faces intersect, we have to look at the 3 connecting vectors of the second face and determine if any of them intersect with the face of the first with the first face. So if we look at our vector D, we don't expect any plane intersection, and this can be indicated by a t, which is equal to a real number not equal to 0 over 0. And once again, geometrical interpretation, because the denominator is 0, so n dotted with d is equal to 0, so n is perpendicular to d. However, n is not perpendicular to the vector from point u1 to p1, so therefore u1 is not on the plane, just by simply the definition of the plane. Now if we check e with pi, we expect a planar intersection, and it is in range, so we have in range meaning t is within the values of 0 and 1, which means that it intersects in between the points. However, it is out of bounds of the face, and we determine that using our coordinate systems here, using a matrix, reducing that, and then we have to check that x1 and x2 are positive, and then that x1 plus x2 is less than 1, and in our case here, x2 was less than 0, so there is no collision. If we check the vector f with pi, we expect a planar collision. Once again, it's in range, so t is between 0 and 1. And we do our matrix, and we find that x1 and x2 are positive, and when you add them, you get a value that is less than 1, using our inequality. All right, and then our last case, a case that we kind of left out, but I talked about, was if t is not in range. So if it's outside of 0 and 1, and I could kind of, you kind of think of having just a value that where the line between 2 points will eventually intersect with the plane, which will almost always happen because you're not there. It's hard to have a perfectly perpendicular plane. So you'll have that, but it doesn't intersect in between the points. So therefore, the face in the graphic, so the face in the world would not intersect. All right, and then a more general case that I didn't provide an example for was if the line was on the plane, where we expect a complete planar intersection. And then as a result, what we have to do is just, what we get here is that t is equal to 0 over 0. And then we just have to check if the vector intersects with any of the bounding lines of the triangle. And we use that use matrices to solve that one as well, which is pretty cool. So yeah, that's collision theory. I'm not gonna call it collision theory because I don't know if this is. I need to refine this just to make sure that everything is actually good, but the principles are here, I think. There's definitely room for, let's say, over in our coordinate systems, there's definitely a possibility that the point is not, that we want to have some leniency for the point not being on the plane, just for floating point rounding errors. So we could kind of have, have an equation of we could have 3 equations and 3 unknowns trying to find that x3 component, and we don't, if we assume that if we don't assume that it's 0, and we can kind of check that it has to be within like negative 0.05 and 0.05. So that's another, or assume x, or don't assume. If we don't assume it, we would just have to make sure that it's close to 0, so that it's close to the plane at least. Because this reduction can be very finicky if you don't have the exact values. So yeah, that's going to be what we'll implement in the future. I'm still working out how I want to represent a lot of this stuff, but I have some ideas. And once again, this will be adaptable for any type of transformation, rotation, whatever, because we can rotate the normal vectors, and we can also rotate the points using matrices and so on and so forth, and get an accurate collision model, which is pretty cool. And once again, I do want to reiterate that this will be a very coarse check, or sorry, a finer check. So we will still keep the sphere, which the sphere will be valid for any rotation, because it's if you just, I mean, I don't know I really don't know how to explain why it is, but if you rotate anything, and it will still be within its bounding sphere. It does not stay true for the bounding boxes. So we can use the spheres as a coarse check, and then determine what faces intersect using it as a finer check, and then we can use the results from that to determine collision reactions, which is pretty cool. So we'll look forward to that. Once again, I still need to figure out representation and write some code, but we will definitely get through it, which will be exciting. So until then, enjoy yourselves. Rewatch this video if you need to. Make sure you got the concepts down. I will definitely provide a link to the GeoGebra, this 3D graph up here, and then I'll also probably export this as a PDF from OneNote, and I'll put this on the GitHub as well, so you guys can read over this. Yeah, until next time, until we start writing code, hope you guys enjoyed, and hope you learned something, and I'll see you guys then. Have a good one.